Section 7.2 focuses on bimolecular nucleophilic substitution steps. Not only are we going to learn about mechanisms, we're also going to learn a little bit about the vocabulary mechanisms here. Bimolecular means that you have two molecules that are going to come in contact with each other. And so because it's bimolecular, that's where the 2 comes in. And then the nucleophilic substitution, that's the S and the N. So this is abbreviated as an SN2 reaction. So reactions that involve SN2 steps are really important in organic chemistry, especially in organic synthesis, which we're going to talk about in Chapter 10. The products of an SN2 reaction might be the compound you want to synthesize. Alternatively, an SN2 reaction might be used to alter the reactivity of a molecule in ways to make it further reactions possible. Because of this central role in synthesis, we will revisit SN2 reactions in chapters 8 through 11. So we're really going to kind of settle down and focus on these nucleophilic substitution reactions. So let's define a few things here. A nucleophile of an SN2 reaction forms a bond to the substrate. And so we have a nucleophile. It's going to form a bond to the substrate. At the same time, a bond is broken between the substrate and the leaving group. The leaving group is the thing that leaves. Okay. This step is said to be bimolecular because it contains 2 separate reacting species in an elementary step. And so the step's molecularity is 2. Okay. And so here are 2 examples of SN2 steps that we see where there are 2 things that react. We have a nucleophile. The nucleophile is the electron-rich species, and it comes out and it attacks the electron-poor species. When it attacks the electron-poor species, these electrons go here, and this group leaves. It's called a substitution because if you look at like the CH3 here, where there was a chlorine before as the 4th bond, now there's an OH. Something has been substituted. Now, just as we saw with the proton transfer steps, an SN2 step is an elementary step, and that means the reactants are converted into products in a single event. Now we can look at this in a free energy diagram of an SN2 step. And so we see our free energy diagram here. So the reaction is progressing through a single transition state where we're showing a generic nucleophile and a generic substrate. Now, both the nucleophile and the substrate bonds here are partial bonds in the transition state. Now remember, we really can't isolate transition states, okay? So transition states are at the top of the hills. If you have like a 2-step and you have a dip, that's where we get intermediate. So this is a transition state. And what we're showing here are the bonds that are forming and the bonds that are breaking as the reaction progresses. Notice that the -1 charge disappears from the nucleophile and then appears on the leaving group as the reaction proceeds. So a partial negative charge is going to appear on both the nucleophile and the leaving group in the transition state. Now, common leaving groups include things like chlorine, bromine, and iodine. Those are conjugate bases of strong acids, HCl, HBr, and HI respectively, because in each case, the negatively charged atom is either relatively large or very electronegative. So they make good leaving groups, and we see those very often. So let me put some words to that. Where we're kind of talking about characteristics of the substrate, we're talking about leaving groups. So in this case, the substrate is the molecule that contains the leaving group, right? And I'm going to abbreviate leaving group as LG, okay? Leaving groups are relatively stable with a negative charge. Okay. Leaving groups are typically conjugate bases of strong acids, like Cl minus, Br minus, I minus. Okay. A nucleophile tends to be attracted by and form a bond to an atom that bears a partial or full positive charge. So common leaving groups also include anions where there is substantial resonance and inductive stabilization of the negative charge. So I want you to look at this leaving group that I'm showing right here. It is not a conjugate base of a strong acid, but I want you to notice that it has resonance, right? And then it also has some inductive stabilization, right? And so that makes it a really stable group, and so it's a really stable leaving group. So it makes it easier for this to leave if it's going to be really stable. These are really stable as themselves. They stabilize that charge really, really well, so they leave, and they're stable, and so that's what makes a good leaving group a good leaving group. Water and alcohols are also common leaving groups too, because they're the conjugate bases of strong acids. So that would be things like H3O plus and ROH2 plus respectively. So a couple of the leaving groups that you're going to see through here. Now I want us also to talk about nucleophiles. The term nucleophile means nucleus loving. It's derived from the Greek. It's given this name because the nucleus of an atom bears a positive charge, the type of charge that we might find on an electron poor atom to which the nucleophile is attracted. So how do we recognize common nucleophiles? Species that act as nucleophiles in SN2 steps generally have an atom with the following two features. It's got a full negative charge or a partial negative charge. So that's a nucleophile. Or it has a lone pair of electrons. And so we have here some commonly, so there's the full negative charge, and here's some common negatively charged nucleophiles shown here. Here's a partial negative charge, and then we can also see here some commonly uncharged nucleophiles, and they have lone pairs. So notice nitrogen, oxygen, sulfur, those tend to make appearances pretty frequently as our nucleophiles. So let's do an example. Can CH4 act as a nucleophile in an SN2 step, and why or why not? Well, here's some questions we need to ask ourselves. Does CH4 have an atom that carries a partial or full negative charge? So the first step to really answer this is that you need to draw the Lewis structure for CH4. Right, and so here's methane, that's CH4. The carbon atom here has a formal charge of 0, but it does have a small partial negative charge because carbon is slightly more electronegative than hydrogen. And so the next question is, does that atom have a lone pair of electrons that can be used to form a bond with another atom? And it doesn't, right? There's no lone pair of electrons on that carbon. So CH4 does not act as a nucleophile in an SN2 step, right? There is a small bit of an electronegativity difference, but it's so small that it's so small that it doesn't even affect the polarity, right? So there's a hydrogen and a carbon here, and we still consider this to be a nonpolar molecule. So it cannot act as a nucleophile. There's no lone pairs, and so that's why. So let's continue and look at SN2 steps a little bit more. I want us to compare a SN2 step to a proton transfer, which we've already learned about. So the electrons in an elementary step tend to flow from an electron-rich site to an electron-poor site. In the proton transfer reaction here, OH minus is acting as a base, but what we see is that these curved arrows, because this is electron-rich, is flowing to something, this proton, which is electron-poor. And it's showing here, right, this initial bond is going to form here, and then this bond breaks, and these electrons go on the chlorine here. In the proton transfer step, the electron-poor species acts as an acid, right, because it's going to donate a proton. Sorry, I pointed at the wrong thing. It's going to act as an acid because it's going to donate a proton. In the SN2 step, now we're down here. On the other hand, the electron-poor substrate is not behaving as an acid because it's not donating a proton, but it's behaving as an electrophile, okay? So we define this as an acid because we have this proton transfer. Here we're not going to have any sort of proton transfer, so we're not going to have an acid. And so we have to have another term for this substrate, and that's an electrophile. And an electrophile is an electron-poor species to which a nucleophile forms a bond. That's it. That's the whole definition. It's written right here for you. So now we've defined nucleophile and electrophile. We can restate a general lesson that we learned in the previous section about the flow of electrons from an electron-rich species, and that's right here. A nucleophile, which is electron-rich, will tend to form a bond to an electrophile, which is electron-poor. And so I've written both of those there because I just want you to really know the terminology well. Now, let's do an example problem. This example problem asks us to draw the SN2 step that would occur between C6H5CH2I and CH3SNA. So, as we go through and do this, we need to ask ourselves some questions. Can any portions of the reactants be treated as spectator ions? And the answer to that is yes. When we look at CH3SNA, we know that Na is a group 1 metal. So that means that the Na plus can be treated as a spectator ion and ignored. And so the reactive species then is CH3S minus, right? And I'm going to go ahead and put those electrons. And I'm going to show the mechanism down here, so I'm going to go ahead and write that right here. Then we need to ask ourselves, what are the general characteristics of a nucleophile for an SN2 step, and which reactant species has those characteristics? So nucleophiles that participate in SN2 steps generally are electron-rich with lone pairs of atoms, right? Or lone pairs of electrons. You're not going to have lone pairs of atoms, lone pairs of electrons. And so this negatively charged sulfur has those characteristics, right? So because we have those lone pairs on CH3S, that's going to react as our nucleophile. So that's going to be our nucleophile. So we've identified our nucleophile. Now, what are the general characteristics of a substrate for an SN2 reaction, and which species has those? The substrate for an SN2 reaction should have a leaving group, right? It needs to have a leaving group. And so what we're looking for here with a leaving group is one of the recognizable leaving groups, right? And so one of our recognizable leaving groups is that iodine. It'll leave as I minus. And so because it leaves as I minus, it's really stable. It's the conjugate base of a strong acid. So we can identify that. So the carbon atom to which the iodine's attached is going to be electron poor. And so when we draw this, the C6H5 is a benzene ring. It looks like this. Then we're going to have a CH2 and then an I. Okay, so this right here is benzene, right? And then this is off of benzene. So this then is going to be our electrophile. So our nucleophile has the electrons, and so it's going to come here and it's going to attack this carbon. The reason we know it's going to attack this carbon is because this is iodine, it's very electronegative, and it's going to pull all those electrons away, and it's going to make that carbon electropositive. So it's going to come in and attack that carbon. When it does, this bond breaks, and those electrons go on iodine. And so what you get is the CH3S is going to be substituted for the iodine. So when we draw this, understand we leave that CH2. It stays there, but now it's going to have a new connection to the S. The reason I know it's going to have the new connection to the sulfur is, look, this tells you it does. These electrons come out and they're going to form a new bond. So where you draw this here, that's the new bond that's formed there. Nothing happens to this, so it's still going to be here, right? CH3. Then you're going to have I minus there, right? So use these arrows to really help you predict your products in these mechanisms. Now, let's talk about more mechanisms. The proton transfer and the SN2 steps have a bond that are formed and a separate bond that's broken simultaneously. Bond formation and bond breaking can occur as independent steps though. And so one of those independent steps is a coordination step. In a coordination step, right, a bond is formed. Now, I want you to look at this. Notice how the single curved arrow in equation both 7.5 and 7.6 depict the flow of electrons from an electron-rich site to an electron-poor site. Bromine here is negatively charged, so that's why it's electron-rich. CH3, C plus, that positive there, tells us it's electron-poor. It also lacks an octet, and it's got that positive formal charge. So negatives and positives like each other, and we're going to show how these electrons come over and attack this positively charged carbon to form the new bond here. Use your arrow to show you the new bonds that are going to be formed. In equation 7.6 here, the chlorine of CH3COCl is electron rich because it bears a partial negative charge because it's very, very electronegative. Whereas the aluminum here lacks an octet. So that guy there, the aluminum, lacks an octet. And is electron poor, right? So the aluminum atom also is made a lot more electron poor because it's attached to 3 chlorine atoms here, and those withdraw electron density. So what happens here is these electrons of the chlorine come over and attack the aluminum. Now, if you remember or recognize this from general chemistry, particularly the acid-base reaction chapter, you would not be wrong. This is a Lewis acid-base reaction, this aluminum chloride one. And I want to remind you in a Lewis acid-base reaction that a Lewis acid, right, accepts an electron pair, right, and a Lewis base donates an electron pair. The product here is called a Lewis adduct. Okay, So in both of these are Lewis acids and bases, right? This one, though, you saw in general chemistry. This was a really common one that we see in general chemistry. The Lewis acid here is the electrophile, right? And then the Lewis base is also the nucleophile here. So, and then of course here's the Lewis adduct as well. So we have seen this before. We just, let me back up. So we've seen Lewis acid base reactions before, and then coordination steps, they fall under this coordination step kind of umbrella for us. Now, we can have coordination steps, right? But we can also have kind of what we view as the opposite, which is a dissociation step or heterolysis. So when we look at this, the formal term is heterolytic bond dissociation or heterolysis. You're going to see heterolysis a lot more than you see heterolytic bond dissociation step. This occurs when a bond is broken and the two electrons end up on one of the atoms initially involved in the bond. Okay. If you want to break this down, hetero here means different, and lysis means to break. So if it broke up there, I had to pause it for just a second. So we just talked about the definition of heterolysis, and so what we're seeing here is that this is going to break into two different molecules here, right? You'll notice that heterolysis steps are the reverse of coordination steps, and heterolysis and coordination steps do not take place in isolation. Okay, these guys are usually one step in a longer mechanism. Now, this is different than that proton transfer mechanism that we looked at, or the SN2. Those will take place by themselves. These two, this coordination and heterolysis, are really the first kind of steps of mechanisms that we don't normally see all by themselves. They're part of something bigger. When we talk about things that involve two or more elementary steps, that part of something bigger, that's referred to as a multi-step mechanism. The reason that these aren't really all by themselves and they have to be part of a multi-step mechanism is because they produce a product that lacks an octet. So this guy and this guy here lack an octet. So that makes them very unstable, right? And so they just don't hang around. They'll very quickly go on and react with something else. All right, so let's look at our next kind of set of mechanism steps. This would be nucleophilic addition and nucleophilic elimination steps. So when we look at these, we think back to section 7.2 at the beginning of this screencast, where we introduced the SN2 step. And then in that SN2 step, the nucleophile forms a bond to an atom containing a suitable leaving group. A nucleophile can also form a bond to a polar pi bond. I want to point out something. This is called a polar pi bond. It's polar because there's a difference in electronegativity between the carbon and the oxygen here. It's a pi bond because it's a double or triple bond. And so that's where this identification of a polar pi bond comes in. What we find with this polar pi bond here is that the oxygen is much more electronegative than the carbon, and so that oxygen sucks away all the electron density, leaving this carbon as partially positive while this oxygen is partially negative. So a nucleophile, which has a full negative charge, will come in and attack something that is partially positive. These polar pi bonds generally are double or triple bonds. You can see an example with a triple bond here, right? Trying to think if there's anything else I wanted to tell you. And this is just the generic form right here. So we see it with double and we see it with triple bonds. We will focus more in on this in the second semester. We'll have entire chapters that are dedicated to the reactions with polar pi bonds. Now, so this is nucleophilic addition, okay? Let's look at nucleophilic elimination. Now, nucleophilic elimination is the reverse of nucleophilic addition. And what we see here are these electrons, which is really negative, come down here to form a double bond, and then there's a leaving group. I like to think of this as being eliminated, like it's gone, poof. And so that's where that nucleophilic elimination step is. Something has to be eliminated. In a nucleophilic addition, something has to be added. That's where the names come from. They give you a clue into what's happening in the mechanism. In the products, the leaving group's atom that was evolved in the initial bond ends up with a lone pair of electrons and an excessive negative charge. But then you're going to see generally some sort of pi bond formed here. So nucleophilic addition steps are often part of multi-step mechanisms that also contain proton transfer steps. We're going to see that in chapter 18 and 19. And then substitution reactions can take place when nucleophilic addition and nucleophilic elimination steps occur back to back, which is chapters 22 and 23. And then if biochemistry is on your horizon, a lot of biochemical reactions also involve nucleophilic addition and nucleophilic elimination steps. And we'll see some examples of that in chapter 19 and chapter 23. So this wraps up for us Screencast 2. We will start Screencast 3, continuing on through our different elementary steps of mechanisms, and we will be introduced to a bimolecular elimination step in our next screencast.